or P3, whatever it is equal to 0 because it's a prismatic joint, so it doesn't contribute at all to the angular velocity of our tool point. So now that we've got our angular velocity Jacobian, we can actually try and plug some numbers into it. So the example we've got here is to find the angular velocity of the tool point when the arm is configured as it's shown in the picture, with joint 1 rotating at 2 rads per second and joint 2 rotating at -1 rads per second, and joint 3, the prismatic joint, is going to be locked at 2 meters, so it's not going to be extending or retracting, it's just fixed. So here we've summarized the variables. So these are our joint velocities, 2 and -1 rads per second, and this is our joint parameter for joint 3, which is locked at 2 meters. So we have our general Jacobian, or angular velocity Jacobian, which has sines and coses in it. What we want to do is sub in the actual numbers. So θ1 in this current configuration is 0 degrees, so cos 1 is going to equal 1 and sine 1 is going to equal 0. So that's why we get a 0 and a 1 here. And so now we've got our Jacobian for this specific configuration calculated. So we can put that down here, and then we need to multiply it by our array of joint velocities. So joint 1, 2 rads per second, joint 2, -1 rads per second, joint 3 is locked at 2 meters, so it has no velocity. Multiply this out and we get our answer here. So joint 1 is going to be moving at, the rotation of the tool point is going to be 0 around the x-axis, -1 rads per second around the y-axis, and 2 rads per second around the z-axis. So what we've got here is we're going to go back to revisit our linear velocity and how we calculate our linear velocity to work out a much easier way, or an easier way of working out the linear velocity Jacobian. So first thing to remember is that the origin of the ith reference frame, as defined in the base reference frame 0, is the first 3 elements of the 4th column of matrix Ti0. So we've got our transformation matrix, which is 4 by 4. It's got those 4 elements in each column. Then what we're talking about here is the first 3 elements of the 4th column of T. And that gives us this origin's location in the base reference frame. So the velocity of the end effector, so the tool point for an end-link manipulator, is simply the rate of change of the origin of the tool point with respect to, so n is the tool point frame, with respect to the base reference frame. So by the chain rule, which is just adding up all the contributions that each joint gives to the tool point velocity, so we're trying to work out the linear tool point velocity, you sum it for all the joints, and for each of them you work out the partial derivative of the rate of change of how the tool point moves in the base reference frame, how that varies with changes in the particular joint variable you're looking at, and then you multiply it by the actual speed of the joint variable, or the rate of change of the joint variable at that time. So for the equation's rewritten at the top. So when you're trying to work out your linear velocity Jacobian, each column in the Jacobian is simply the rate of change of the tool point origin in the base reference frame with respect to the rate of change of that particular joint velocity, or that joint variable I. So in other words, the ith column of your linear velocity Jacobian is showing the movement of the end effector, or the tool point, as is caused by the joint velocity q dot I. And this leads us to an alternative method of finding linear velocity Jacobian. So that fact's just reiterated here. It's showing that the ith column shows how the tool point moves based on the joint variable velocity q dot I. So we can look at the two cases. So this is the prismatic joint case, and we're going to look at the Revolute joint case in the next slide. Prismatic's pretty easy. What we can say is that how much, or the velocity of the tool point in the base reference frame, so this is how much the tool point is moving within the base reference frame, is simply the rate of change of the variable for the prismatic joint. So basically just how fast the prismatic joint is extending or retracting times an axis defined here. So this axis is the axis of actuation of joint number I as it's defined in the base reference frame. So this whole thing is bringing it back into the base reference frame, so where everything's being calculated in the same reference frame. So if we rewrite this, the velocity of the tool point is z I minus 1, 0 times q dot I, which is the joint variable velocity. So if we switch this around a little bit, this corresponds to the Jacobian matrix component, because we've got it in our general form. We've got a tool point velocity equals something is here, times your joint velocity. So this thing is going to be your Jacobian component. So your Jacobian component for joint I is just z I minus 1. So there's an example next slide which is going to sort of illustrate this in a much more visual way, but we're going to deal with the linear velocity Jacobian for a Revolute joint here on this slide. So once again, the ith column of the Jacobian shows the movement of the end effector caused by the joint velocity that we're dealing with, joint I. A Revolute joint causes a different type of movement of the end effector, and because joint I is a Revolute joint, it rotates around its own z-axis. So the z-axis for joint I is z I minus 1. So that's the axis it's rotating around, and that's defined in that z I minus 1 axis frame. What we want to do is define everything in the original reference frame. So the end effector velocity, this is once again just the tool point velocity defined in the base reference frame, is the rotational speed of it times the displacement. So what does this all equal? Well, the rotational speed that's contributed by joint I is the joint velocity, which is an angular velocity, rotating around the z I minus 1 axis, times the difference between where reference frame of the tool point is and the reference frame of this particular joint. So if we rearrange this a little bit, if we take the q dot I outside of the brackets down to here, we get this expression here. Once again, we have this general format of velocity of the tool point equals something times the joint velocities. And this something is the Jacobian components again. So we can say that the Jacobian component contributed by a Revolute joint is this term down here. So here we've got a 3-link, 3-joint robot arm example again. Joint 1, joint 2 are Revolute, joint 3 is Prismatic. And what we're going to do is work out the linear velocity Jacobian for this arm. So the part of the Jacobian that's contributed to by prismatic joints is just simply the z-axis of that joint I as defined in reference frame 0. And for the Revolute joints, it's the zi-1 axis as defined in reference frame 0. Cross product the difference between the tool point origin and the joint origin. So we've got our transformation matrices, all the relevant ones. So the first two are both going to be involved with joints 1 and 2, which are Revolute. So they're going to be involved with this one. And the third one, which relates prismatic joint, is going to be related to T30. And this is our general form for the cross product down here. Useful to have this as a reference, although you should learn it pretty quickly. So this is how you cross product two vectors together. So just to reiterate, if we want to work out z components, for instance, z1 in terms of 0, well, it's just simply this part of the matrix here, and our origin of reference frame 1, defined in reference frame 0, is just this part of the matrix here. So this is what we're going to be pulling out of the matrices to do the calculation in the next slide. So for joint 1, I'm just going to scribble it on here. So for joint 1, we have, it's a Revolute joint, so joint V1 equals zi-1. zi-1 is z0 in this case. Z0 is always just 0, 0, 1. And this is multiplied by the cross product of ON and O-1. So the cross product of, so ON is 03 because the tool point is in reference frame 3. So ON is going to be this part. That's ON. And OI-1 is going to be the reference frame of the original, which is just 0, 0, 0, because the original reference frame is at 0.000 defined compared to itself. So it's just going to be negative L3 C1 S2, negative L3 S1 S2, and 3 minus L3 C2. And then we've got to use this fancy cross product rule. So the first row is BZ minus CY, so it's that minus that, which becomes L3 S1 S2. The second row is CX minus AZ, so CX, which is minus L3 C1 S2, minus AZ, which is 0. So that's our second row. And our third row is AY minus BX. So AY is that minus BX minus that. So that's 0. So that is going to be our joint GV1. So that's what we've got here. I calculated in the last slide, and that's our JV1. You can do the same thing for JV2. The O3 is going to be the same, but this is going to change, and this is going to change. So those two are going to be different.